like merge sort, it is a recursive divide and conquer algorithm. The difference is that heap sort does all the work up front, or sorry, at the end. Oh, sorry, I'm getting mixed up. Merge sort does all the work at the end. So in merge sort, when you're dividing a list into two lists, that's no work at all. When you're merging those lists back together, you're doing a selection sort. That's where all the work occurs, is at the end, at the conquer part of divide and conquer. Quicksort is the opposite of that. Quicksort does all the work in the beginning, in the divide stage, and then the conquer stage, the merging stage at the end is easy. Quicksort happens to be the fastest comparison-based sort for arrays. And I mean fastest in practice, and I am including the constants hidden in the big O notation. So this is just something that's been observed to run really, really fast in practice. And yet, I'm going to sound like I'm contradicting myself here, but its worst case running time is n squared. However, if it's implemented correctly, it virtually always runs in big O of n log n time. So for all practical purposes, it is an n log n time algorithm. And I'll show you later in the semester how to use probability theory to analyze it and show that it runs in expected n log n time. But there's always a tiny probability that it might run in n squared time, probably much smaller than the probability of you being killed by a meteor in the next hour, so probably not a big thing to worry about. I'll mention that usually Quicksort is significantly faster than merge sort for sorting arrays because it has nice tight inner loops that give you a really small constant in the big O. But if you're sorting linked lists, Quicksort doesn't necessarily have the same advantage. Sometimes merge sort runs faster than Quicksort. For sorting linked lists, it depends how you implement them. All right, so the way Quicksort works is we're given some unsorted input. We're going to choose some element, some item in it, to be what's called the pivot element. And the pivot element is going to be used to partition the input into two separate lists, a list of items that are less than the pivot and a list of items that are greater than the pivot. So we start with an unsorted list I of n input items. We will choose a special item that we will call a pivot item, and I will call it V from that list. I'll talk about how to choose the pivot later. For now, just choose an arbitrary number out of the list. And then we're going to use that pivot to partition the input into two lists. I'm going to call those lists I1 and I2. And they're going to be unsorted lists. We haven't sorted them yet. But they will differ in one important aspect, which is I1 will contain all the keys that are smaller than the pivot's key. And I2, the second list, will contain all the keys that are greater than the pivot's key. So what about keys that are equal to the pivot? Well, those can go into either list. We'll talk more about that later. And in fact, how we do this is going to be a crucial decision, but it's going to be different for linked lists than for arrays. So that's why we're going to put off talking about that till later. However, whatever you do with items that have the same key as the pivot itself has to be treated specially. The pivot does not go into either list. And that's very important. So that is how we partition items. Now that we've partitioned them, what next? We sort these two lists recursively. So now we sort the first list, all the keys that are less than the pivot, by calling Quicksort. And we'll assume that Quicksort works correctly and gives us a sorted list, which we'll call S1. And we'll do the same thing for I2. We will sort I2 with Quicksort, yielding a sorted list that we will call S2. Once we've got those sorted lists, then it's easy. You just glue them together. Either all the items in S1 are sorted and they come before all the items in S2. So you just glue them together with a pivot in the middle. The recursion will bottom out when we reach a list of size 0 or 1. That's where we stop. Any list of size 0 or 1 is sorted, so we just return it back up the recursion. I'm going to give some examples of this, but before I do, are there any clarification questions about this algorithm? Okay, so well, let's see what this algorithm does. So I'm going to give you a couple of examples. I want to show you what can go right, and then I want to show you what can go wrong. So let's start with what can go right. Here is an array of 7 items, 4, 7, 1, 5, 9, 3, 0. For now, I'm going to use the rule that the pivot is always just going to be the first item in the array. So when I start, I'll make 4 my pivot. So what I do is I walk through the array from left to right, skipping the pivot, and each item goes either into the list of items that are less than the pivot or the list of items that are greater than the pivot. So start with 4 as the pivot, then there's a 7. The 7 is going to go into the list of items to the right, because it's bigger than the pivot 4. Then there's a 1. 1 is less than the pivot 4, so I'm going to put that in a different list of items that are less than the pivot. Then there's a 5. 5 is greater than the pivot. Then there's a 9. 9 is greater than the pivot. Then there's a 3, which is less than the pivot. Then there's a 0, which is less than the pivot. So now that gives me those lists I told you about, I1, keys that are less than the pivot, I2, keys that are greater than the pivot. I'm going to sort those two recursively. After they're sorted, I'm going to glue them together with the pivot in the middle. So here's the pivot. V. So now I call quicksort recursively on those two arrays. I have an array 1, 3, 0. I pick the first key to be the pivot, so 1 is the pivot, and then I partition the rest of the array into keys that are less than the pivot, like 0, and keys that are greater than the pivot, like 3, and I have the pivot in the middle. So once again, here's the pivot, here's the unsorted array I1 recursively, here's the unsorted array I2 recursively. But when you have an array of length 1, it's sorted, so we're done with the recursion on that side. On the other side, we'll do the same thing. 7, 5, 9, we say 7 is the pivot, we make a list of keys less than the pivot, keys greater than the pivot, and we put the pivot in the middle between them. So there's an unsorted array I1 and our unsorted array I2. Again, those only have one key, so they're sorted. So basically now we're done. We just need to take these numbers that were created as we went along and glue them together into big lists. And that's sorted. So in this example, things worked out really well. We got a recursion tree for quicksort that's really nicely balanced. And so this was pretty fast. This was as fast as merge sort. Let's look now at what can go wrong. One of the things that can really, really go wrong is, I told you that this rule that we use is that we're going to just pick the first key to be the pivot. Well, it turns out that's a really bad idea if your list is already sorted. So I want to sort this list. It's already sorted, but I don't know that. Someone just gave me a pile of numbers. I don't know that they're sorted. I just throw quicksort at it, make sure that they're sorted. So here what happens, well, we pick the first item to be the pivot, and that's a 0. So now we take all the keys that are less than 0 and put them on the left-hand side, take all the keys that are greater than 0, put them on the right-hand side. Well, all the keys that are less than 0, there aren't any, so we get a subarray of length 0 on the left. All the keys that are greater than 0, well, that's everything except the pivot. And we put the 0 in the middle. So that's our unsorted array I1 on the left is empty. Our unsorted array I2 on the right is still pretty full, and the pivot is between them. Now we recurse on the right-hand side. We pick the leftmost key to be the pivot, and that's a 1. So now you'll notice we'll get the same kind of disaster all over again. And you can see we're getting a pretty unbalanced split here. When you get an unbalanced split, that's just not a good thing, and I think you can see where this is going. It's going very, very slowly to being a sorted array, but not nearly as quickly as we would like it to. So this is kind of a mess. It's, you may notice, turning into a quadratic times sorting algorithm. And there we're finally done, but it took quadratic time to do it. So this sucks. It's a disaster to use the pivoting rule that we always choose the first item to be the pivot if the array is already sorted. This won't do it all. We need a better pivoting rule. So you see we span the range from, you could get a perfectly balanced tree if you're really lucky, and the whole thing will run in n log n time, just like merge sort, because you're going to have about log n levels of the recursion tree and at most order n time per level. And if things don't work out well, then you can get theta n squared worst case time. So let me write down what I just said. When input is already sorted, choosing the pivot to be the first item is just a disastrous policy. Any questions about how Quicksort works before I talk about how to choose a better pivot? The first one is n log n, for the same reason merge sort was, that if you happen to get perfect splits, then you have big O of log n levels of this recursion tree, and at every level of the recursion tree, it is order n time per level. And most of that order n time is doing the partitioning. The partitioning step takes linear time. Other questions? So I want to talk about how to choose a better pivot. The answer might surprise you. Researchers have tried lots of things, and the time-tested thing that works really well and reasonably quickly is to pick a pivot randomly. Flip a coin. It's actually really surprising how well this works and how it tends to work better than anything non-random that anybody has thought of. For instance, when I talked about this tree being order n log n time, that is actually the expected running time, not the worst case time, which is n squared, but the expected running time in a formal probabilistic sense. You can prove using probability theory that if you choose a random pivot, that Quicksort will run in expected n log n time, and I will actually show you a proof of that later in the semester. But the important thing to understand for now is that on average, and I'm using that term loosely, I'm not being mathematically precise here, but on average, you can expect a 1/4, 3/4 split. Now, you cannot expect to get a perfect 50-50 split like you can get in merge sort. You do not quite that well. On average, we're going to get 1/4 of the items on one side of the partition, 3/4 of the items on the other side. Half the time we will actually do worse than that, meaning even more unbalanced. Half the time we'll do better than that, meaning more balanced. But even though it's unbalanced compared to merge sort, and that means you might get a deeper recursion tree, Quicksort has some advantages that still make it faster for sorting arrays. If you want to know why you get a 1/4, 3/4 split on average, I'll just mention that Goodrich and Tomasia have an explanation of that in section 11.2.1 of their book, if you have the 5th edition. If you have a different edition, you'll have to figure out what section that's in. But they show that the average running time in a probabilistic sense is in n log n. And again, I will talk about that later in the semester. One other thing that's worth mentioning is that picking a random pivot works pretty well in practice. When you have still a relatively large array, like if you've got at least 50 keys or so to sort in the recursion, the level of the recursion that you're at, researchers have found that it can be even better to pick what's called a median of 3 strategy. That means instead of picking one random key to be your pivot, you pick 3 random keys, you look at which of those 3 random keys is in the middle, the median, and you use that as your pivot. And again, you can analyze that with probability theory and show that that will tend to give you better balanced splits. But it takes a little longer to choose the pivot, so it's only worth doing if you're sorting at least 50 numbers or so. All right, I left a lot of details out of how to do quicksort, especially how do you deal with keys that are the same as the pivot. And we're going to see that you want to do that differently for linked lists than for arrays, because there's tricky things you have to do to make in-place array quicksort work. So let's start with linked lists, because that's easier to understand. So quicksort on linked lists. What do you do with keys that are equal to the pivot? Well, we could just put them all into one of the lists, like I1. So let's see what happens if we do that. Suppose we put all items with the same key as V into list I1. Will quicksort work if I do that? Yes, yes it will. Will it work fast? Unfortunately, no. And here's why. One special case that you should always worry about is, does my sorting algorithm run fast if all the keys are the same? So here's an array full of 5s. Well, it's already sorted, but we don't know that. We don't know it's all 5s. We're just blindly running our sorting algorithm on that list. And maybe it's not all 5s, maybe it's just mostly 5s. But what happens if I use this rule that says all keys equal to the pivot go into I1? Well, then what's going to happen is all these 5s are going to go into I1. And the pivot goes out separately, and thank goodness for that, because otherwise this would run forever. And I2 will just be an empty list. And so now you've got a recursive quicksort call on those 5s. And again, it doesn't matter which one is the pivot. You're going to do the same thing over again. And you can see where we're going here. We're going for n-squared performance again. So this policy is no good. Putting all the keys equal to the pivot in I1 means n-squared running time when all the keys are the same. Not acceptable. We need to do something else. All right, so here's the better solution, but only really works for linked lists. This is not going to work for in-place array quicksort. For linked lists, though, we can just partition I into 3 linked lists. And let's call them I1, items that are less than the key, I2, items that are greater than the key, and IV is going to be items equal to the pivot key. And what the hell, let's throw in the actual pivot too. So IV will contain the pivot, V, and all the items with the same key as the pivot. So now what will happen if I try to sort this array of all 5s? We'll get 3 lists. I1 will be empty, because there are no keys less than 5. I2 will be empty, because there are no keys greater than 5. IV will contain all the 5s. And since they all have the same key, we do not sort IV recursively. It's already sorted. So now we're going to have a quicksort that runs in linear time if all the keys are equal to each other. And that's great. Let me just show you a slightly more sophisticated example, because we also care about having fast performance when almost all the keys are the same, but not all of them are the same. So here's an array that's just mostly 5s. We will still separate out the keys that are less than 5 and the keys that are greater than 5, and we will sort those recursively. But all the keys that are equal to 5 They get pulled out into a separate linked list. They're already in sorted order, so we do not have to recursively call quicksort on IV. We're done with that, and now we can do the rest of the sorting really fast because there's not much sorting left to do. And then, of course, when we're done, we'll concatenate the recursively sorted list S1, the doesn't need to be sorted list IV, and the recursively sorted list S2 to get the output. And so with this little change, we add one extra list called IV. We've made a quicksort that was really, really slow when you have lots of keys that are equal to a sort that's really, really fast when you have lots of keys that are equal. Any questions about that? Mm-hmm.
What about this is specific to linked lists as opposed to arrays?
Well, if you're doing arrays and you're doing in-place arrays, meaning that you cannot have a whole bunch of arrays, but you've just got the one that you were given as input, then it is not easy to partition into 3 separate lists that are all in the right position in the array. If you try writing the code for that, you'll find it's a messy pain. You can do it if you think hard enough, but then you're also going to find out that it's slow, that the big O factor is much bigger than it is for the code that just partitions into 2 lists. And therefore, you lose the advantage of quicksort, which is it's usually the fastest sort. The only real way to understand that is to actually try to write the code and see what happens. But trust me when I say that partitioning into 3 arrays like this, 3 different sets, in place in an array, is complicated and therefore slow. Other questions? I'm going to talk about how we do quicksort on arrays. And one thing you'll see about this is that when you're just partitioning into 2 lists, you can write really tight code that does this very fast. And that's part of the secret of why quicksort just happens to be the fastest comparison-based sort in practice. So in-place quicksort is really fast. It's tricky to code correctly. And it is very easy to write a buggy version by mistake, and Goodrich and Thomasia did exactly that. So if you have the textbook, at least the first 5 editions, I don't know about the 6th edition because I haven't seen it yet, but in the first 5 editions, their quicksort code on arrays takes n squared time if all the keys are equal. We're going to try to do better than that today. Our input to our array today will be, our input to our code today, our quicksort code, will be an array that I call A. And because quicksort is recursive, and I want to do recursion on this array, I have to be careful about that. I want to write my quicksort in such a way that I can tell it to just sort part of the array and not sort the whole array. So I'm going to give you 2 indices, low and high, and I only want quicksort to sort the items that are between A low and A high. And this allows me to have quicksort recursively call itself to sort just part of the array. At the top level, we want to sort the whole array, but we'll be recursively sorting parts of it on the way down. So our algorithm works like this. First of all, we choose our pivot V randomly. And then I want to partition the array into 2 pieces, I1 and I2, keys less than the pivot, keys greater than the pivot. It turns out to be easiest and fastest to do that if I get the pivot out of the way. So I do that by moving it to the end of the array. In particular, I swap it with the last item in the array. So again, I'm just moving the pivot to the end of the array, or the sub-array, so that all the other keys that I want to partition are contiguous, and I can partition them really fast. Next thing I'm going to do is I'm going to employ two array indices called I and j. I am going to have I initially set to low -1, where low is the first key I want to sort. I'm going to have j initially set to high, the array index that now contains the pivot. And the idea is that as I go through, I and j will sandwich, so to speak, the items to be sorted or to be partitioned, not including the pivot. I'll show you what I mean by that in a minute, but basically all the keys we want to sort are between index I and j, not including index I or index j. And we will move I and j inward toward each other while satisfying the following invariants. We insist that all items at or to the left of index I have a key that's less than or equal to the pivot's key. And we will insist that all items at or to the right of index j have a key that's greater than or equal to the pivot's key. So let me demonstrate this now. Actually, let me draw that higher. Suppose that the array that I want to sort looks like this. Three, 8, 0, 9, 5, 7, 4. And the index low is the index of this array element here, the 3. The index high is the index of this array element here, the 4. I randomly select a pivot. Let's suppose I select the 5. So 5 will be my pivot. Now I want to partition this array. I want to have all the keys that are less than or equal to 5 before all the keys that are greater than or equal to 5. So the very first thing I'm going to do, as I said, is I'm going to swap the pivot with the last item in the array. So the 4 and the 5, I swap them. Everything else is in the same place as before. Now I set a pointer I that points to low -1, meaning it actually points to the spot in memory before the first item I want to partition, and j will point to the pivot. And when I have I there and j there, what that means is that I am working now on partitioning everything between those two, not in counting I, not counting j. I'm partitioning these things in the middle. And now I'm going to take I and j and move them in toward each other while enforcing these invariants. And so the idea here is I will advance I forward until I reach a key that's greater than or equal to the pivot. So again, here's my array, 3, 8, 0, 9, 4, 7, 5. I advance I forward to the 3. That's less than the pivot. So I keep advancing I. I reach the 8. 8 is greater than the pivot 5. So I stops there. Then I will do the mirror image thing with j. I will decrement j until I find a key that's less than or equal to the pivot. So I move j back one step to 7. 7 is greater than the pivot. I move back another step to 4. 4 is less than the pivot, so j stops here. So I has now reached a key that's greater than the pivot. J has now reached a key that's less than the pivot, so I swap them. So I swapped the 8 and the 4, and that helps partition them. I want all the keys less than the pivot on the left, all the ones greater than the pivot on the right. Now I'm going to keep going. I'm going to keep advancing I forward until I find another key that is greater than the pivot. I'm going to keep moving j backward until I find another key that's less than or equal to the pivot. And this time something interesting has happened. I and j have actually crossed over. They've passed each other. When I and j meet in the middle, that means that we don't have to do any more swapping. So we're going to repeat this loop until I is greater than or equal to j, and then we stop. And when we have reached that point, now we will swap the pivot back to the middle. Specifically, we swap it with I. So I'm going to take the pivot. Remember, the pivot is this 5 over here on the far right. I'm going to swap it with I, and that gets the pivot back between the keys that are less than the pivot and the keys that are greater than the pivot. And I accomplish that by swapping the 5 with the 9. And now I have an unsorted array I1 that is keys less than or equal to the pivot. I will sort that recursively. I have an unsorted array I2 that is keys greater than or equal to the pivot. I will sort that recursively. So I want you to observe what the pseudocode that does this looks like. And I've got that further on. I have the wrong one there. 1 second. So this is the pseudocode for Quicksort. It'll be in the lecture notes. I recommend that you study it carefully later on. The main thing I want to point out right now is the lines of code that do the partitioning. You'll see that there are these do loops with smaller do loops in the middle. I probably can't write on this, so this is not the right program to use. No. Let me try something different. So the step that does the partitioning, this does almost all of the work, is that do loop there. So this loop does what I just said. It advances the pointer I forward repeatedly. It advances the pointer j backward until it finds items that you can swap. So you have an item that's too big on the left, you have an item that's too small on the right, you swap them, and here's the swapping step here. And then you keep going until the I and j pointers cross each other in the middle. And the really important thing to note about this is those inner loops are very, very small. So look at this do loop here. All it does is it advances the pointer I with the statement I++, and then it does one comparison. It compares that key to the pivot, and then it does that over and over and over again. So this is a very small, simple inner loop, and that means the compiler can make it run very, very fast, especially if you have a good optimizing C compiler. And likewise, the loop that goes backwards and does J is almost as simple and runs very, very fast. The reason why Quicksort has a smaller big O, or a smaller constant hidden in the big O than other n-log n sorting algorithms is because those inner loops are so small and simple, and they just run really, really, really fast, especially if you have a good optimizing compiler. And that really is the secret to why Quicksort is considered to be the fastest of the n-log n algorithms and is used a lot in practice. So again, when you're reading the lecture notes afterwards, study the pseudocode and make sure you understand how the whole thing works, but especially focus on those boxes. That's the reason why this is so fast. It's just because of the simplicity of the inner loop beats the simplicity of the inner loops of merge sort or heap sort, which have much more complicated inner loops. So one thing I want to especially focus on as well is how do you handle items that have the same key as the pivot? It's really tricky to handle these right, and as I said, Goodrich and Thomasia have gotten it wrong in all 5 editions of their textbook. So, I mean, what are they doing wrong? Well, when they have 2 keys that are equal, they don't split it. So they don't manage to subdivide them evenly into 2 equally sized sets. So if you have a bunch of 5s, what Goodrich and Thomasia would do is they would have, remember the I starts here, the J starts here. You start moving the I forward and the J backward. The way Goodrich and Thomasia would do it is the I goes all the way over here, stops there, and now you're done. You put all of the 5s into the left-hand partition. And with a pivot on the right, and you can see we're on our way now to n squared land. We don't want to go there. So what can you do instead? How can you be smarter about this? What we do in the version of Quicksort I just gave you is that when I is marching forward, or J is marching backward, and you hit a key that is equal to the pivot, then you stop. So, I will take 1 step forward and hit a 5. 5 is equal to the pivot, so we stop. J will take 1 step backward. It'll hit a 5. 5 is equal to the pivot, so we swap. So we stop, and then we swap I and J. So I and J get swapped. We swap this 5 with this 5. That may seem insane, like we're wasting time swapping a 5 with a 5, but it's actually not. Because then what we're going to do is we will move the I 1 more step forward. We will move the J 1 more step backward. We'll swap again. We swap the 5 with a 5. We move the I forward and the J backward. We swap again, the 5 with the 5. We move the I forward. We discover that we are done. And now you'll notice that the I and the J are in the middle. So we're going to get a recursion where we quicksort these 3 5s, another recursion where we quicksort these 3 5s, and the pivot goes in the middle. And hey, we have a perfectly balanced split because we were smarter about the rules for what we do when we hit a key that's equal to the pivot. And now we're going to get an n log n sort instead of an n squared sort because we're getting these perfectly balanced partitions when all the keys are equal.